All right, as we get started today, let's go ahead and review some things we've talked about recently. We've been talking a lot about matter. What is matter, Audrey?
It's what stuff is made of.
It is what stuff is made of. In fact, it's the stuff,
Mm-hmm.
right? But stuff would be a less than scientific definition. So if you were asked on a quiz or test, what is matter? You wouldn't say, well, it's stuff. You would say,
The amount of.
now you're getting the definition of mass. Kendall?
The amount of mass.
That's mass. Mass is the amount of matter in something. What is matter?
Anything that takes space.
Oh, okay, there we go. Michael's streaming at his phone screen. Anything that has mass and takes up space is matter. So since you take up space, like we said, you matter. And you have mass. However great or small the amount. You have mass, you take up space, you are matter. We said that all matter has a property called inertia. Okay, Audrey, here we go for redemption. What is inertia?
Inertia
It's a tendency that matter has.
is,
If that gets you started on your definition, it's a tendency.
stuff that's moving stays in motion.
Okay.
Stuff at rest stays at rest.
Okay, there we go. Okay, so matter in motion, stuff, matter, okay, in motion tends to stay in motion, and matter at rest tends to stay at rest unless either of you?
Affected by like an outside force.
Yeah, unless some outside force acts upon it, right? So, I mean, this water bottle, once I set it there, it tends to just sit there. Tends to just sit there unless some outside force acts upon it, right? And then it goes flying and then that's all the water bottles fall, right? But yeah, it just tends to stay at rest unless an outside force acts upon it. Now an outside force acts upon it, so it moves. And once I throw it, it would tend to just keep going in a straight line at a constant speed, but for a force that maybe the wall exerts, or if it doesn't make it all the way to the wall, maybe something gets in the way of the water bottle, I don't know. and like paper airplanes. And gravity, of course, is an outside force that's pulling down on, in fact, what do we call the pull that gravity exerts upon an object's mass? Weight, very good. We said mass is how much stuff or matter is in an object, so the more stuff that's inside Audrey's body is what gives her more mass. And the more she stuffs into her body, the more mass she has. And she's not fat, for the record. In case people are like, is he making a fat joke? She's not fat, it's fine. But there's another definition for mass. What's our other definition for mass, besides the amount of matter contained in an object? Either of you.
The amount of inertia.
She redeems herself. The amount of inertia an object possesses. We also talked about density. What is density? I don't know. Correct. Just kidding. What is density, Kendall?
Well, it's a ratio
It is.
of mass and volume.
It's the ratio of an object's mass to its volume. So, for instance, I have this bottle of water, right? Well, if I were to drink all the water, save the bottle, and then fill it with shaving cream, it would feel lighter, wouldn't it? Right? It would look full. It would still be full, but it would weigh very little comparatively because the shaving cream doesn't have as much mass for the same amount of volume. There's not as much stuff, right? There are little air pockets in it. You might remember back to your geology section of junior high Earth and Space Science. Remember that far back? Did you have Miss Morse for that class? Okay. I was trying to remember. That's right. She's been here long enough. She's had you all the way through up to this point. And there was a rock that can actually float. Do you remember what that was called? It's a volcanic rock, an igneous rock. Pumice, yeah. And so pumice, it floats because it's all full of holes. So it has a certain volume, but because of all the little holes in it, it floats, unlike most rocks where you drop them and they go down. And I remember when I had we had a little kiddie pool. We were out on the back deck, and Chloe was really little, and we were playing, and she noticed that my flip-flop floated. And I held up a big rock. I said, do you think this will float? She said, and I dropped it. Sure enough, it didn't float. I said, yeah, because it's heavier than the flip-flop, isn't it? She's like, uh-huh. And I picked up a little bitty rock. Do you think this will float? It's not very heavy. Yeah, it'll float. And it dropped. It was just like, puzzled. And I did not explain Archimedes' principle at that point. I just let her puzzle on it, and let her try to think that one through. But you'll get the brain thinking scientifically, right? 2 years old, is it too early, is it? Well, anyway, all right. Pray for her. We also talked about something called specific gravity. That kind of leads into the rocks, okay? And what is specific gravity? Audrey? By the way, if you're wondering, where's Michael? He's watching right now with the rest of you. Anyway.
Well, you have to measure it with the sample of your standard.
Okay, it's a comparison, right? Compare is the key word, or relative density, right? Comparing the density of something to the density of a standard. So, for instance, the flip-flop has a different density than the little bitty rock. The little bitty rock has a density greater than water. Little bitty rock still sinks. Flip-flop density less than water, it floats. But you're comparing densities, right? Comparing the density of some object to the density of a standard. We said for solids and liquids class, the standard is? And for gases, it is hydrogen. Then yesterday we began looking at, really I guess 2 days ago, began looking at matter in a little bit more depth. No, that was yesterday. Matter in more depth. And we said the most basic building block of all matter class is the atom, the atom. And we said a chemical combination of two or more atoms is called a? Maybe. A molecule. A molecule. Now, let's suppose we have a substance, and within the substance, every single molecule is exactly the same. Now we have something called a? Compound. Good, a compound. Every single molecule is exactly the same. I don't know, maybe this is why, in jail, everybody's got the same jumpsuit on, and maybe that's why they refer to it as a compound, everybody looks exactly the same, I don't know. But every molecule is exactly the same. It's a compound. That's one type of pure substance, but there was another pure substance we looked at yesterday. Either of you remember that? An element. And Kendall, do you remember how an element differs from a compound? It's still a pure substance, so there's still this idea of everything's the same, but it's not every molecule that's the same. Every atom is exactly the same. And I gave you the example yesterday of pure oxygen, right? Well, obviously they couple together in oxygen atoms of O2, but even pure ozone, right, which would be O3, right? Pure ozone, if I got pure ozone from somewhere, I've created, but every molecule, every atom is still an oxygen atom. So therefore we would still have an element there in a sense. Whereas the compound, every molecule is the same. So for instance, we said pure water. If everything is H2O, well, you have different types of atoms, hydrogens and oxygens, but as long as the molecules are all the same, we have the compound. I guess ozone technically, that couldn't be considered an element because if you broke it down, you could break away and then you'd actually have a different substance, which would be oxygen. So never mind, I take that back. Trying to get creative. Don't get creative. Then we talked about a couple types of mixtures. And we talked about mixtures in which there's a nice, even, uniform distribution of different types of stuff. There's all different stuff, different types of molecules, whatever, but at least they're evenly distributed. So you don't find a little pocket of lots of this, or a layer of this, or a clump, I like that word, of that. Okay, everything's evenly, uniformly distributed throughout the mixture. What would we call that, either of you? Actually, it's homogeneous. Homogeneous is used in a slightly different sense, but it does sound better, doesn't it? But a homogeneous mixture, everything's evenly distributed throughout. And I gave an example of, well, when you buy it, hopefully, yes. It doesn't naturally come that way, but milk has been homogenized, it's true. Kool-Aid, for instance, you stir it in real good and it stays that way for a while, if you do it right. And then we said it is possible, though, if you don't mix the Kool-Aid very well, or the milk sits for too long, and it begins to separate, you begin to get these clumps or layers, and then you have not a homogeneous mixture, but a heterogeneous mixture. We also looked at states of matter, and we said the most abundant state of matter in the universe, we believe, is plasma. And we said plasma, we believe, really is just, what, Kendall?
Really highly ionized gas.
A really highly ionized gas that's really, really hot, okay? And we said specifically two columns off that periodic table. Do you remember which ones they are that ionize at high temperatures and only at high temperatures?
Noble gases.
The noble gases and help? The halogens. The halogens and noble gases will ionize only under extremely high temperatures, and then that's what we call plasma. Again, that's where you've got the electrons stripped away, which doesn't happen easily. That can be plasma. And again, why would that be the most abundant state of matter in our universe? I mean, you don't just go around encountering plasma every day, right? How is that, Kendall?
It's found in the stars.
Yeah, we believe that's what the stars are, and if that's the case, then that would make it the most abundant state of matter in our universe, since most of the universe isn't matter at all, it's just empty vacuum. However, on Earth, which state of matter do you think would be the most abundant? Certainly not plasma, right? We don't find it every day on Earth. We can create it, we can use it, right? They even have the picture there in the book of the plasma cutter, right? Because of its abilities. But what do you think would be the most abundant on Earth, Audrey?
Gas.
Well, believe it or not, the gas in our atmosphere, it only extends up a couple of miles, and then it begins to get really sparse, right? That's why even Denver, Colorado, you're about 3 miles high at that, or no, mile high. Mile High City is what they call it, Mile High Stadium, for instance, a football fan. And but they have breathing apparatus for players because their bodies can't get the same amount of oxygen they're used to up that high. Gives Denver kind of a home field advantage once their guys get used to it. So it only extends up a little ways, which actually means it's not as abundant as we might think. So that takes you down to 2 more states of matter.
Sun.
Well, if you look at our planet, most of our planet isn't actually covered with land, right? And even the land, think about it, you've got plants, but what's inside plants? Liquid. Right? And of course, water extends many miles deep in places, covers most of our Earth. We have rivers and lakes all over where you would find even solid land mass. So liquid is actually the most abundant state of matter here on Earth. But obviously plasma for the universe, or at least that's what we believe. Now, with gases, how would we characterize gases? What makes gas unique?
It has no defined shape or form.
Good, and it's in fact the only substance that has no defined, which one, shape or volume?
Shape, volume.
Yeah, this has no defined shape either, but no defined volume, right? This has a defined volume. How much liquid do we see? That much. If I pour it out, it'll spread out, but it's still the same amount of liquid. Gases can literally fill space. So gas is unique in that they have no definite volume, also no definite shape. Obviously liquid, Audrey,
Has no shape, but it has volume.
has no definite shape, but it does have a definite volume. Now, because gases and liquids have no definite shape to them, a term for it to get down in your notes, this term fluids, F-L-U-I-D-S, fluids, refers to both to both liquids and gases because they have no definite shape. They can flow, right? Hence the term fluid. They are flowable. Solids, on the other hand, they have a defined shape. They have a defined volume. They don't just flow. Now, people are like, well, what about when you melt gas or when you melt a liquid? Well, now you're turning it into, or when you melt metal. Well, you're turning it into a liquid at that point, okay? So, yes, you can heat things and cause them to change states of matter, and we'll look at that when we talk about thermodynamics later. But as far as in their natural state, at normal, what we would consider normal temperatures, the solids have definite shapes and, of course, definite volumes. All of that pretty much, other than the term fluid, which I just had you jot down, all of that should be reviewed from the past. Let's move on then to what actually composes matter. And we said the basic building block of matter again is the atom. And so let's talk a little bit about the atom. An atom is primarily, if you could look at it microscopically, primarily empty space. That's unfortunate. Primarily, how many fragments did I get? Lots of fragments. Lots and lots of fragments. We're going to talk about brittle substances later in the year when we talk about deformation. Chalk. Brittle. All right, steal her chalk. All right, so largely empty space, but there in the very middle of the atom is a hard core, if you will. And that hard core is called the nucleus of the atom. Proportionally, it's tiny. An atom is already tiny, but the nucleus is proportionally tiny. Yet within the nucleus are tinier objects. And these tiny objects, there's two what are called subatomic particles. So the things that compose the atom. Now you, in chemistry, I believe last year, studied the different theories of the atom, right? Where you started with, I believe the original theory was all matter is made of these tiny little hard spheres called atoms. And it's just a little blob that's hard. And then they realized, well, actually, things can go through atoms. And so then I think it was the plum pudding model that they came up with, and there's this idea that it's almost like a jelly-like substance with maybe a hard center. And then they realized, well, no, that's not even it. It's just empty space with the electrons buzzing around. And then they had the electrons going around in exact patterns. And then they went to, well, it's more kind of the cloud or orbital model. And, you know, again, when you're studying something that tiny, as you make different discoveries, you realize, well, we thought this, but based on what I'm observing, this behavior tells me that can't be true. Again, they can't actually quite see it, but based on behaviors, this is what they're come up with. Within the nucleus of the atom, two subatomic particles, and what are they? Just from last year's memory, or perhaps from your reading a couple nights ago? Protons and neutrons. And mathematicians and scientists alike are lazy. So what we'll use is, we'll use notations for these, right? A proton is a P with a little plus like a superscript, and neutron is a little N with a superscript 0. Because a proton has what charge class? Positive. Proton's positively charged, neutron, neutral charge or no charge. Buzzing around the nucleus, depending on the atom itself, depending on what substance we're talking about, would be infinitely small, virtually massless little objects that are buzzing all around. I say buzzing, they don't really make noise. And those little buzzy objects going around are called electrons. And of course, they provide the balance, if you will, charge-wise, and electrons are notated E with a little negative. Okay, so when you see those notations, you know what I'm referring to: protons, neutrons, and electrons. If we were to notice, and you'll remember this from your study of chemistry last year, every different substance on the periodic table, every substance known to man, has a different number of protons in the nucleus of the atom. In fact, it's the number of protons that give the atom its characteristics. It defines what it is. So the number of protons gives us what's called the atomic number of the atom. The number of protons literally is the atomic number of the element or of the substance. If you change that number of protons, you change what you have. Remember that from last year? But I told you the electrons are virtually massless, and then all around is, other than where the electrons are buzzing, it's just kind of empty space. The nucleus is where the mass of the electron comes from. And of course, an individual atom, the mass of the atom comes from. An individual atom has incredibly small amounts of mass, right? It's tiny. But the mass that is in an atom is believed to all be contained simply in the nucleus. Well, since the nucleus is protons and neutrons, the combined number of protons and neutrons gives us what's called the mass number of the atom. The mass number of the atom. Now, here's the only thing about the mass number, because as you look at the periodic table, normally, however many protons you have, that's how many neutrons you should have as well. That's normal. You have 7 protons, you'll have 7 neutrons. 7 and 7 makes 14, so the mass should be pretty much 14. Now, technically, protons and neutrons' masses aren't exactly one atomic mass unit each, but you'll notice some of these are just absurd. For instance, you look at some of these, and you're like, well, that's not even remotely close to double. Well, sometimes the number of neutrons could be changed, and you'll remember this from last year as well and from your reading. You can change the number of neutrons in an atom, often by bombarding atoms with additional neutrons to make them inherently unstable. This is used in, you're talking about half-life radiometric dating and things like that. So since neutrons can be added, possibly taken away, I've never really heard of that, but I'm sure they could. Since neutron counts can change, what we do for the mass numbers, we'll actually take all the known isotopes based on their frequency and average the numbers there with the atomic mass units to get mass number. So the mass number isn't always exactly equal to normal protons and neutrons. Otherwise, the mass number would simply be double the atomic number. Okay, but it's usually relatively close. But you do need to know the term isotope. An isotope is a substance that has gained or lost, I suppose, neutrons. Usually gained. The number of neutrons is different than normal. Therefore, the mass number is different, but not the atomic number. So an isotope has a different mass number than the normal atom, but it's the same atomic number as that same atom, for instance. Carbon-14, probably the most common example, right? It's bombarded with 2 additional neutrons that it can hold, so it's got more mass than a normal carbon atom, carbon-12, yet it's still carbon. Same atomic number, still 6, but different mass number. It's an isotope. Does that make sense? There's another I word, though, and it's the I word is ion. So let's talk about ions for a moment. In a normal atom, however many protons you have, well, that gives you your positive charge. You're going to have that same number of electrons, which gives you the balancing negative charge. So for instance, again, we take carbon, 6 protons, 6 electrons. It balances out. Again, I've never really heard of carbon losing electrons. There are other things that do, or gain electrons. That's not particularly normal with carbon. But certain substances can gain or lose electrons. We actually talked about that when we talked about the plasma, right? Gaining or losing electrons. If electrons are gained or lost, it creates imbalance in the force, right? And so what happens is if electrons are lost, then the light side is winning. And if electrons are gained, the dark side was winning, okay? And so we've got, and Michael's like, I don't get it. Don't worry, Michael. All right, so a proton positive charge, well, you don't gain or lose protons. That changes the whole substance. A gain or loss of electrons is where the charge will change. A loss of electrons produces a positive charge, and we call that ion specifically a cation. So ion is a general term for any charged atom. The cation specifically is positively charged because of a loss of electrons. A gain of 1 or more electrons increases the negative charge and results in something called an anion. Now, I believe everything I've just said is reviewed from chemistry, right? So none of this should be that hard for us. Any questions on that? All right, let's delve a little deeper. And this I'm not positive that you learned in chemistry or not. We're going to go a little into the realm of modern physics here. I said most of this course is going to focus on the traditional physics, the classical physics, right? But we're going to delve just a little bit in here, and we're going to go to the year 1905 when Albert Einstein proposed his theory of relativity. Prior to Einstein's theory of relativity, it had been assumed that the total energy in the universe is constant. Energy cannot be created nor destroyed. And it was assumed that total mass in the universe was constant. Matter could not be created or destroyed, only changed into other forms. And there was this thought that there was some connection between mass and energy, but it was Einstein who put it all together with this famous equation, E equals mc squared. And by so doing, by relating mass and energy with the speed of light, that's what the C represents, the speed of light, 3.00E8 meters per second is the accepted value for C. But with this equation, he showed that mass and energy can affect each other. So that, consider for a moment, if I were to solve the equation, for instance, for m, I would be dividing away c. I'd say that the mass of an object is equal to the energy it possesses divided by the speed of light squared. Where's an obvious implication? What if I increase the energy of the object? Then the mass will increase with it. What if I decrease the energy of an object? Decrease the mass. Interesting. A couple of different effects that we see from this. One of these is something called mass gain or nuclear mass gain. A couple things here. One of them, the question was asked earlier about photons, right? These little particles of light. For the longest time, light was believed to be a wave, then it was believed to be a particle, and then they realized it couldn't be a particle, it had to be a wave, but somehow it was still a particle. And Einstein, with his theory of relativity, settled this and said, well, because as energy increases, mass increases, light which travels at such excessive speed can in some ways be thought to have this tiniest little bit of mass to it as well. Not just a wave that carries energy, but actually has a little bit of some form of mass with it. And he called these little particles of light photons. Now, the mass is, for all practical purposes, negligible, but it's still somewhat present with these particles of light that are in a beam of light or a stream of light, this stream of photons as light passes through a vacuum or as light exchanges energy with other particles. It's thought of as the photon, for instance, strikes your skin, for instance. It releases the energy and therefore its mass goes away. Kind of weird, right? So photons streaming from the sun hit your body, energy is imparted to your body, which makes you feel warm, and you're like, oh, it's hot out here in the sun. And then, of course, the mass is gone. It doesn't add mass to you because in releasing its energy, it now has dissipated. And, of course, they're small enough it wouldn't have mattered anyway. Another implication of this is with an electron. This is, I believe, observed that they've accelerated electrons. Now, electrons travel fast, but they don't travel nearly as fast as the speed of light, okay? But if electrons were accelerated near the speed of light, I believe they've accelerated electrons to about 90% the speed of light, and electrons' virtually non-existent mass, negligible mass, has actually doubled. Now, it's still really, really tiny, but still we've seen a mass increase as we've increased the energy of an object. So, for instance, Kendall's like, I'm tired of being little, I want to be big. If you ran really, really fast, near the speed of light, you would gain mass, theoretically. Could you go that fast? No, you burn up, okay? But if you could, then you would be gaining mass. Also, on the flip side, there's this idea of nuclear mass defect, that if you could get energy to go down, you would decrease mass. For instance, you've learned about potential energy and kinetic energy, right? If I chuck the water bottle through the air, it has kinetic energy. If the water bottle sits on the edge of the table, there's a little bit of potential energy. It's not acting yet, the bottle's not moving yet, but with just the slightest disturbance, the bottle could be in motion. So there's a potential energy, a gravitational potential energy, and it's pulling on the bottle, right? So that with the slightest disturbance, now gravity's able to act, right? So potential energy has this idea of, as objects are far apart, there's more and more potential. For instance, right now I'm just barely above the ground, there's a little potential. As I raise it higher and higher, there's more and more potential because at the moment I release the bottle, it'll be able to move even faster and move further, right? Well, if I set it on the ground, and let's even knock it over, now how much potential energy does it have? None. If somehow I could smush it into the ground a little ways, that would be less than zero energy, okay? The particles within the nucleus of an atom are held very tightly together by a very strong force. We actually call it the strong force. Okay, held by a very strong force, pulled into each other so that they have negative or less than zero energy level. Because that's true, the mass of the nucleus is less, at least this has been observed in some of the heavier atoms, less than what you'd expect. For instance, you know the whole is equal to the sum of all its parts. But the mass of the nucleus is less than the sum of all its parts by just a tiny bit. We refer to this as nuclear mass defect. Nuclear mass defect. And again, it's because the energy is so low. But again, all of that was a mystery until relativity explained it. Energy levels drop to sub-zero. Mass will begin to drop to sub the sum of all of its parts. So a couple of interesting implications. We're not going to go much deeper there with relativity, simply because there's a lot that is still theoretical. But just a few examples, I suppose, of how this relationship between mass and energy works. However, what I've described to you so far has at least been observed. Okay, what I've explained to you has been observed. Now I'm going to get into some things that haven't been observed. And let's talk a little bit about some atomic theory, next section in your notes. Atomic theory. This is something that hasn't been observed, but we believe currently this to be true. Now, in 5 years, will we believe this to be true? I don't know. The kilogram just changed. I mean, anything's possible with stuff that hasn't been concrete. But here's some things that we believe. Okay, so with atomic theory, right, we've talked about subatomic particles, right? Proton, neutron, electron, your subatomic particles. Well, we want to talk now about elementary subatomic particles. Elementary refers to the most basic it can get, the simplest level. I mean, obviously now we have kindergarten, but in the old days, kids started school in first grade. That was why it was called first grade, because it was the first grade, okay? And so elementary referred to, this is where we start. This is the baseline. Elementary subatomic particles are those particles which cannot be broken down any further. And yet, protons and neutrons currently, we believe, are not elementary subatomic particles, but rather could be broken down into further particles called quarks. And I believe you talked about these in chemistry last year as well, that they believe protons and neutrons are composed of elementary subatomic particles called quarks. Now, because protons and neutrons are composed of quarks, or at least we think they are, the quark theory seems to settle some things for scientists right now. We refer to them as hadrons. Hadron is a term to refer to anything made of quarks, which, protons and neutrons, because we have to come up with names for things. All right, so quarks. Now, the idea is that there are what we call up quarks, which are positively charged, and down quarks, which are negatively charged. And the way they've made the math work out here is there are 3 quarks in a proton, 3 quarks in a neutron. The up quarks have a positive 2/3 charge. Down quarks have a negative 1/3 charge. And if that's true, then if you had 2 positive 2/3 charges and 1 negative 1/3 charge, that all comes out to a positive 1 charge, and there's your proton. You see this picture there for you on page 27. No, we do not believe the quarks are different colors, but for illustrative purposes, it works great. And then we believe the neutron is composed of 2 down quarks and an up quark. And that neutralizes it out. And so therefore, we have these quarks. And this also, they thought, well, here's how this helps to explain. Why would a positive proton and a neutral neutron hold together? For that matter, there are other protons there, right? Like charges repel. There's got to be something that holds them together. And that's why they came up with the quark theory. The problem is this. There's 2 positive 2/3 charges. And there's only a negative 1/3 charge in that proton. Shouldn't the stronger positive charges repel, even if they're both attracted to the weaker negative charge? How does this hold together? And I envision in my imagination, I envision a scientist after a long day at the laboratory coming home and sitting down, perhaps frustrated by this conundrum. And how do these quarks hold together? Because with what we know about the law of electric charges, that shouldn't be the case. And he sits down and he's clearly perplexed. And he's got a little girl. I picture somebody like Chloe, maybe who's 3 years old, or somebody like Renee, and full of energy and life and vigor and creative thought. And comes over and says, "Daddy, what's the matter?" And the scientist says, "I don't know, honey. It's just been a long day in the lab, and can't figure out how these things are sticking together. Like, they shouldn't be able to stick together, yet they do. But if I throw out my theory about them, then how does the whole thing fit together?" And then we'd be back at square one. It's like, I just got to figure out how these things stick together. They stick together like they glued on? I got it! There is some kind of particle called a gluon that helps to hold these things together. I don't know that that's where the term comes from, but I just, imagination, it just sounds too perfect, right? But the gluon is the substance that they believe, or the particle, whatever, that holds the quarks together. Again, it's theory. Have they observed a gluon? No. Have they observed quarks? No. But based on the way things behave in the nucleus of the atom, they believe that this is the case. Now, I remember when I was in school and first learned about quark theory, it's been around a while, that I was like, well, I got this. -1/3, -1/3, -1/3. -1, there's your electron. Wait a second. Because of the quarks, the neutron and proton have mass. The electron is so tiny it could not possibly be made of quarks. So even though the math works out great, it doesn't work for the mass. So we can't say that an electron is made of quarks. So because it's not made of quarks, it is not a hadron. An electron is called a lepton because it's not made of quarks. It's called a lepton because it is not made of quarks. Now, it's not the only lepton. There are a few other leptons we'll look at. There's something called a positron, which we'll look at tomorrow, that they believe is a lepton. The neutrino, they believe, is also a lepton, because it's not made of quarks. We'll look at the neutrino tomorrow as well. But a lepton is anything not made of quarks. And a hadron is anything that is made of quarks, which is the proton and the neutron, which quarks held together by the gluon. Kind of sounds like the hip bone connects to it. Anyway, that's where we're going to have to leave off, because you guys have to get ready without Michael's help. Some people's kids. Without Michael's help to get ready for pizza day and snack cart, making money off of small children. So I will let you go after you copy down your homework, and we'll pick up with more of this in our next lesson. Homework for this evening is to read pages 25 to 31. Read pages 25 to 31. On page 31, answer questions 18, 19, and 21. On page 31, answer questions 18, 19, and 21. There is a test coming up on Tuesday. If you're watching on video, that's lesson 12. Lesson 12 will be your first test. That'll be over chapters 1 and 2. Tomorrow, we will wrap up chapter 2. Monday, that's lesson 11, we'll be reviewing for the test, and then the test on Tuesday in lesson 12. All right. Once you got the copy down, you are dismissed. Have a wonderful rest of your day. Oh, hold on.